Welcome to the thermodynamics lesson on heat engines and efficiency. We're going to start our lesson with talking about efficiency, and to do that, let's use this applet, this simulation, to discuss a situation that we're more familiar with regards to efficiency, and then make a connection to efficiency in physics. Here we are at our simulation, and what we have is a guy that's going to shoot free throws here. We'll get him started, and he's going to shoot 25 free throws. And if I asked you what is his free throw efficiency, how would you determine that? Well, you can see here he's up to 12 shots and just about got 10 more to go there. And which number here, which percentage represents this shooter's free throw efficiency? Obviously this player looks like he plays for Trumansburg, and you of course would pick the 48% that represents his free throw efficiency because he made 12 out of 25 shots, and 12 out of 25 would be 48%, or 0.48. Well, that's a good start as far as understanding efficiency is concerned. Now let's take that concept back and apply to how does this relate to physics efficiency? A great way to think of efficiency in general is that efficiency is the number of times you are useful divided by the number of attempts to be useful. And if you wanted to express that as a percentage, you'd multiply by 100%. In our free throw example, the number of times the free throw shooter was useful was 12. The number of times he attempted to be useful was 25. And so 12 divided by 25, 0.48 times 100 would be 48%. It's no different in physics. So if we take, in physics, efficiency, symbol for which is lowercase e, and we say, okay, in physics, as far as energy is concerned, useful energy is called what? Well, useful energy is called work. Attempted useful energy would be energy input. So efficiency would be work, because that's how much energy was used to be useful, divided by energy input, which is the total amount of energy available to be useful. Our symbols for that in thermodynamics, well, in physics in general, work is capital W, and in thermodynamics, energy input is Q subscript H. That is the amount of energy, heat energy, supplied by the hot reservoir. Often in problems, you'll hear the term absorbed used. So energy absorbed from the hot reservoir. What that is the total amount of energy available to the heat engine, and W represents the amount of useful energy done to perform work by that heat engine. Now, another way to think about work is that it would be the total amount of energy available to do work minus the energy wasted, not available to do work. We call this QH minus QC. QH, again, is the energy absorbed from the hot reservoir, total amount of energy available to do work. QC is the amount of energy expelled to the cold reservoir, or in other words, it's the amount of energy wasted that was available to do work but was expelled to the cold reservoir instead. A good way to think about this is to think about the engine in your car. Your engine in your car is a heat engine. So QH is the amount of energy supplied by the hot reservoir. In other words, the amount of energy supplied by the gasoline that's going to be burned in your car, in the pistons of your car, in the cylinders of your car. QC is the amount of that energy wasted to the cold reservoir, or in other words, the amount of that energy that came from the gasoline that goes out your tailpipe and is expelled to the cold reservoir, which is the environment outside. Also included in that would be heat energy that is absorbed by the engine itself or lost to other sources. But all of that would be a QC value. And again, we would divide by QH there, which again is the energy absorbed from the hot reservoir. So again, work, another way to think about work is the amount of energy available to do work minus the amount of energy lost trying to do that work. Now, sometimes we'll also see a variation of this equation in which they distributed the QH value, and so QH divided by QH would be 1 minus QC over QH. That's a really simplified way to calculate the efficiency, and if you already knew one or the other of the QC or QH values and you knew the efficiency itself, or vice versa. Okay? All right, we also have a way to calculate the maximum efficiency possible by a heat engine, and we call that the Carnot efficiency. Again, the Carnot efficiency is the maximum possible efficiency that a heat engine can operate at. Now, if you think about that, the maximum possible efficiency would be determined by the total amount of internal energy available minus the wasted internal energy divided by the total internal energy available. Well, what's an indication or a way to measure that internal energy? And that, of course, is temperature. So we have the temperature of the hot reservoir minus the temperature of the cold reservoir divided by the temperature of the hot reservoir equal to the Carnot efficiency, which we show as an E subscript C. Again, if we distribute the TH divided by TH is 1, and TC minus TH would be your other side of your equation there. One thing to keep in mind when calculating Carnot efficiency is that your temperatures have to be in Kelvin in order to do this, the absolute temperature scale. Okay, moving on. Let's talk about heat engines. And this is a great diagram, and you have this diagram in your problem set. I would encourage you to have that out, looking at it as I go through this discussion. This is how a heat engine operates. And this has a cycle in it, step 1, step 2, step 3, step 4, in a clockwise direction here. Let's start at step 1. The heat engine absorbs heat from source at temperature 1, and the gas expands. And the gas expands from volume V1 to volume V2. This process is shown on the PV diagram as for process A to B. And over here, we would draw an arrow showing that it's going from A to B. Process 2, we have a heat source that is removed. Okay, so you can see that the heat here was being added to that. In your car, this would be your spark plug igniting the fuel mixture, okay, which creates heat. Now the spark plug is off, so the heat source is removed. The gas continues to expand and cools to a temperature T2. And this, as the gas expands, it expands from volume V2 to volume V3. So in process BC, we continue to go down away from B towards point C. Now step 3, the cool gas is recompressed from volume V3 to volume V4, and the heat goes to sink at T2. In other words, what that means is, what do they mean by heat goes to sink? is that heat is removed from that cylinder, from that container. This is typically done by the valve in your piston in your car opening and allowing that heat to escape. Okay? And that's where it becomes expelled to the environment. So from process CD, we would have an arrow showing that it goes away from C toward D, from volume 3 V3 to volume V4. Lastly, process V4, the cool gas is isolated and compressed, heating back to temperature T1. Notice here we're still in an insulated state. There's no heat being added or removed. And then what happens, of course, well, let's finish this first. You get a very high increase in pressure in a very short, over a very short volume decrease. And that's a decrease from volume V4 back to volume V1. And then inserted is a gas oxygen mixture. The spark plug ignites again, and the cycle starts all over again. Okay. One thing to note here for this heat engine is that you note that the cycle on the PV diagram is in a clockwise direction. That the four processes take place in a clockwise direction. For a heat engine, that will always be in a clockwise direction for a heat engine on the PV diagram. And if it went in the opposite direction, that would indicate to you that that was a refrigerator, which does the exact opposite of a heat engine. Heat engines produce heat, and refrigerators produce cold. And the opposite would take place if these arrows were all pointed in the counterclockwise direction, and we are traveling from A to D, D to C, C to B, and B to A in one complete cycle. That would be a refrigerator. Something to keep in mind as you're looking at PV diagrams. If they're talking about different directions, a clockwise cycle is a heat engine and a counterclockwise cycle is a refrigerator. All right, that'll do it for our lesson on heat engines and efficiency. If you have any questions, make sure you jot them down and ask in class tomorrow.